we have a request to do Fall 19, Test 3, Part 4, Question 3. Here it is. It's a hydroboration of an alkyne, the terminal. Terminal because it's the end of a chain. I hope you haven't forgot Bu is a nice short form for butyl. Butyl, although it doesn't matter here because Bu doesn't change in the whole deal. So, but it is butyl. And pi has to attack which atom, the B or the H? Electronegativity of B is 2.0. H is 2.1. You attack the less electronegative atom always if you have a choice. And here it is. And judging from the next part, I'm going to go from the underneath. Because the next part has the H coming to which carbon? More substituted. Switch that first arrow to underneath so they didn't cross these arrows. You do not lose points for crossed arrows, so don't worry about that. Syn addition, which one puts the H and the B on the same side? I'm going to be clear. H and the B are on the same side here. Check. H and the B are on opposite sides here. No good. They're on opposite sides. That's anti. This reaction's syn. Why? Both of these bonds happen at the same time. Any mechanism where both of the bonds happen at the same time is syn, with the new groups on the same side. These are on opposite sides. This has the wrong regioselectivity. It put the B on the more substituted carbon. So that's just wrong, wrong, wrong. Okay, so we got that. We have the arrows to prove it. And now it's on to step 2, where we have 6 steps, followed by tautomerization, because this is an alkyne and not an alkene. But the 6 steps are identical to chapter 6, where it was an alkene reacting. Step 1, acid-base. Lone pair on the OH minus attacks the proton in hydrogen peroxide. This is step 1. You generate OO minus. Gray's no good. OOH with a minus and a lone pair to make a bond to which atom? To the more positive boron. And generates this boron that has 4 bonds. Boo. I'm going to draw butyl one time just so you remember. Bu stands for butyl. So 1, 2, 3, 4 goes to a C double C that has B on it with 2 cyads. B also now has O bonded to O bonded to H. B now has 4 bonds. B alternates between a charge of 0 and then -1 and then 0 in the next step, which is step 3. No, don't say step 3 before you wrote step 2. It's got to get down to 0 again by losing one of the 4 bonds. You're going to break the CB and make it CO. Clearly, C must be bonded to O sometime in this mechanism. C is currently not bonded to O. So this is a rearrangement, and it happens so that the weak OOH bond breaks. OO is a weak bond always. Lone pair repulsion. So now you have Bu bonded to a C, double bonded to a C that's now bonded to an O. The O is still bonded to the B, the boron B. Boron's back to 3 bonds, back to no charge. And I think I'm consuming a lot of space here. I need to I want to see if I can fit it on the screen, and the way I'm starting to draw large, it's not going to happen. There you go. 4. Oh, I got to remind you, you also made another product at this time. It's OH minus, hydroxide, and it has a minus. The second time you generate an O minus, you do the same thing that you did the first time you generated an O minus. You attack the B. And this is the initiation of the O exchange on B. You're putting this O on so you can take the other O off in the next step. So we have Bu bonded to C double C that has O bonded to B with 2 Sia groups and a purple OH, which makes boron have 4 bonds again. That's a minus. Get the stray purple thing here. And that's it. We put one O on so that in the next step we can take the other O off. Take the other O off. If this bond breaks, the electrons go towards the more electronegative atom. That's what more electronegative atoms do. Step 5. You got your Bu bonded to your double bond, bonded to O that now has a minus. And you've got H bonded to O. You better show the bond, because step 6 is acid base. You better show the bond to the H. There you go. I can definitely see that happening, but I don't see the other product happening just yet. How am I going to make this O lose an H? I'm going to use this base. Step 6 is acid base. Step 6 generates this O minus and an enol. Alkyne attached to O, attached to H. Enols have a pi that's less stable. Oops. Yeah, that's it. Less stable than a carbonyl pi, because O makes stronger bonds than C. And this one's catalyzed by an acid-base pair. Every tautomerization you do must be catalyzed by an acid-base conjugate pair. We're dealing with hydroxide in this mechanism. I see it on the arrow. That's your base. HO negative. Put it in black, I guess. What's the conjugate acid of HO minus? It's HOH. Put it somewhere. Somewhere. And the base does what bases do. It takes a proton. The alcohol proton from the enol. The sigma between the O and the H resonates towards the carbon to become a pi. We call that a carbonyl. That's your carbonyl happening. And the old pi breaks and picks up a proton from the conjugate acid in your catalyst. So we got to learn the tautomerization. That's step 7 there. I'm not going to number it. We use those numbers 1, 2, 3, 4, 5, 6 to help us remember the oxidation steps. And 7 is only necessary if you have an alkene attached to your alcohol, which you do. Otherwise, you'd be done. And that'd be the chapter 6 reaction. So we got that. And we didn't do circle. We kind of implied that we circled this product by doing a mechanism with it, but just to be safe, let's circle that one. Circle the major product formed in each step. And explain. Explain. Okay. Sin addition. Sin addition. Let's see. And why is it sin? Both bonds happen at the same time, exactly. And there's another part. Markovnikov. Oops, I typed it like we say it, not spell it. Markovnikov, because more electronegative H goes to more. What's the word that says there's more carbons attached? Substituted C. And all of that is the answer for B. So I want to make it clear that's the answer for B. And we'll circle everything for B here in yellow. That's not even the end of the answer for B. That's only for that circle. Oh my goodness. That's for that circle. And the other circles are a little more straightforward answer. Here's the other circle. We like the aldehyde here. And all you have to do is say this. Enol O oxygen becomes carbonyl. During, what's the magic word? T N ION TAU Tautomerization. And that's enol oxygen becomes carbonyl during that. So you're not going to pick the one where the enol oxygen's on the wrong carbon, right? Notice end carbon has the O. End carbon has the O. Don't pick the product where the second from the end has the O. That's the wrong product. Okay. A lot of good stuff there. A lot of points. And that's all we got for that one. See you on the next one.